code runs, and I get reconstructed signals, but it doesn't work perfectly.
Maybe you have seen other courses calculating the transition line parameters like inductance, resistance, capacitor, those kinds of things. I think you guys have one course that they talk about those kind of things. And we'll talk about that one today, how we can calculate the inductance and capacitance, those kind of things, to figure out how we can model the transmission line. And the next chapter we'll talk how this is a kind of parameter model. Where you see how much is the F, how much is the C, how much is the R, how the transmission line. If we have a vector, we have a bunch of conductors. How we can calculate those values. But the next chapter we will talk about the system. Hey, we have a transmission line now. There are different models. There is a short model, there is a medium model, and there is a long model. We'll look at those models to see how we can use those models to model a transmission line. And after chapter 5, which is not in this book, we are going to talk about the system modeling and per unit system. If you look at your book, the per unit system, they explain it in chapter 3 when it's the transformer. I'm going to leave it for system modeling after we finish the transmission line and we know the transformer. And the other element of the system is the generator, and motors. We'll see how we can model those things. We call it single line diagram. In the last chapter, I'm going to cover those kind of things. Hopefully, we'll be able to cover everything. We may have to come one weekend. I'll see a little bit further down the road to see should we come for maybe for 2 hours or not. To make sure we can cover all the material. Already we gave up on the power flow. So I don't want to give up any more material. So if you look at every conductor, it has a resistance, right? And we know basically how to calculate the resistance of the conductor. Resistance of the conductor it has a very simple equation. Resistance calculation for conductor. We call it R. Is the symbol we use for this one. We say RDC. I mean DC resistance at temperature T. We call it is equal to rho or sigma. L over S. Or some people they write it this way. They say L over, right? Either way, you can see. This book uses this equation, to calculate the resistance. Now let's see what we call it RDC, and the T. There are different things we need to talk about, here. If you look at later on, when I get toward the end of this chapter, there is a table I'll show you. They write RAC, AC value of the resistance, and we have a DC value of the resistance. I think all of you are familiar with the Hall effect, right? If you have a conductor, this is a cross section of conductor, right? And we have some current going through this one. The current is pretty uniform everywhere, right? The current density is pretty uniform everywhere. Right? If the current is DC, right? So basically we are using all the area of this cross section, right? But if you have a AC current, there is a frequency, right? And what does it say? The Hall effect or a speed effect. What does it say?
It'll mostly travel around the outside.
The electrons tends to go through the surface of the conductor, right? So if you look at the cross section, it's the DC, and if you look at the AC, outside there are more current, inside there is less current. If I can show you one final little model I did for a doctor when I was in GM for working, and I can show you exactly this one, to show because of the frequency, the current is going to go around the conductor. Like in the middle we have less current. So what's the result of this? Can you tell me what's the result? Let's say this is the same conductor. Same conductor, we pass the AC current and we pass DC current. Can you tell me?
Less net current.
Why higher resistance to the AC?
Less surface area.
Less surface area. If you look at it here, so this let's assume there is no current here. There is some here, but let's assume basically the surface area for you is this area, right? Or this one is this area, right? But here we are using all the area. In this one, the surface area is smaller, right? So basically, the AC resistance is higher. This is one of the effects. You call it a steam effect or I don't know, frequency effect. It causes the resistance to be higher. The other thing we're going to look at it is temperature. How the temperature is going to affect the resistance. Temperature is, if you look at this rho of T is equal to PT will rho at temperature 2 is equal to rho T1 times T2 plus T over T1 plus T. So the rho value will change with temperature. This T is a constant number for example, copper, for either silver, for aluminum, or whatever, right? So this one you will find from table. Then if you look at your book, this table, for example, table in page 175, table 43, it gives you T for example, copper is 234.5. For aluminum, for example, is 228.1. So this T is a constant number for this different, conductor, these different materials. Now you can see if the temperature goes up, the rho is going to go up. So the rho goes up means you are going to lose the resistance is going to go up. So this is another element from the resistance. If you look at the transmission line, summertime, because the temperature is higher, so we are going to have a higher resistance, so it's going to be a little bit more of loss. The T2 is the temperature. See, for example, we know at T1 30-degree temperature is, for example, 1 ohm, for example. We want to know how much is that, for example, 60 degree. We want to know how much is the rho at 60 degree. The T is a kind of constant number. For example, it depends on the material. For example, if it's copper, aluminum, silver, whatever, As I said, the table will give you that value. So you can calculate the new rho for example, copper at 60 degree or 70 degree or something, whatever. Now the third effect, we need to look at it is if you look at all the conductors, they are not like AC conductors. See, usually you see a conductor like this, right? But how many of you have you kind of used a stranded wire? If you look at it, the wires they're pretty straight. They are like what's it called, a spiral, like this. The wires go like this. You know what I'm saying? They are twisted. My point is the wires are twisted. What is going to happen? What is the result of that? For example, you have 1 meter of twisted wire, right? If you make it, straight, for example, it's going to be 1.1 meter, right? Because the length is higher, right? So the twisting also is going to cause the resistor to be higher. If you look at all the transmission lines, I cannot draw the picture here, but if you look at all the transmission lines, the wires are like this. Usually they have before going to this one, we have different materials for the conductor. We can use copper, we have seen copper everywhere. We can use aluminum. You haven't seen that much of aluminum, but in transmission line there are aluminum, very wide. And we have silver, and we have different materials. Among all this one, silver is the best conductivity wise. It has the minimum rho. So the minimum rho, the better, right? So basically, it has less resistance. But what is the problem with the silver? It's expensive, right? They use it for some important, products, they have to go with that and they use that one and it makes it more expensive. But even, for example, a simple wire, it doesn't work. So you put the silver there, to build a simple wire. Now, the next two, if you compare, copper is better than aluminum. And the table 4, what's the number? Table 4.3 in page 175, you can see all these numbers, for this different material. If you look at it, you can see copper is better than aluminum. But for most of the application, you see, you guys have worked with is copper wire, now. But for transmission lines, they don't use the copper. Can somebody tell me why? Huh?
Too heavy?
They are heavy, exactly. Think about it. There is these two towers. There are these big cables, these wires that are going to go. Copper is very heavy. So the weight of copper is going to cause problem for the tower. They go with aluminum, right? It's much lighter than the copper. So, but what's the problem with aluminum? The resistance is a little bit higher. But what's another problem with the aluminum? It don't have the mechanical strength, right? It can break easily, So to fix that problem, they do this. They put a kind of a steel here. One strand is a steel, which is pretty, the mechanical wave is pretty strong, right? And now they put the rest of the conductor or a string like this around. So the middle one is steel. The middle one is steel, and now there is these are aluminum. Wire, so they may put all this for the steel, and from here they start to put the aluminum, wires, based on how strong one to have the wire, the cable, right? They can put more steel. The equation for the how many conductor we are going to have is given by N is the number of conductors. Number of conductors is equal to 3x2 minus 3x plus 1. This is the number of conductors. This is the layer. So basically here, we have a two-layer system, right? Two-layer cable, right? So if you put 2 here, it's going to be 3 times 2, 3 times 4 is 12, minus 6 plus 1 is 7. You have 7 conductors. This is the way we build these cables, for transmission line. But in general, we have a DC resistance, which we can calculate it this way. Still, DC resistance could be a function of temperature, which we can calculate the new value by doing this equation. And spiral, length of the wire can affect this L. When we have an AC resistor, the L is longer than what it is. For example, 1 meter cable is using 1.1 meter, of the conductor. And the last one is the Steen effect, which it doesn't affect the DC resistance, but it affects the AC value. AC value, and usually when the frequency goes very high, for example, in power electronics, they go to, for example, 100 kilohertz switching. I may show you the result if I can find it. I may show you what I have for GM time. You can see the current is going through the surface of the conductor, and in the middle there is no current. That one is a bad thing. It's going to increase the power loss of the system. They call it a Steen effect or, frequency effect or something like that.
So X is layers. Like, so in this example that you've drawn, would that be just one?
No, 2. There are 2 layers. 1.
Oh, okay.
So if you have 3 layers, N is going to be how many? And it's going to be, if you have 3 layers, it's going to be 3 times 9 minus 6 plus 1, 27, 28, 22. 22. Already we have 7 here, right? So it's going to be how much? Layer 3. Layer 3 is going to be 22 minus 7 is going to be 15, right? Okay, you should put 15 here. It's going to be like the number of conductors here. number. So basically, you just have 15 over there for the layer number. You can see that this one is getting bigger and bigger. The more layer, it's going to get bigger and bigger. Now, we talked about the resistance. The next one, so resistance is pretty simple, and there is the unit is ohm per meter, or they go with the ohm per kilometer, or I don't know whether a system, if you use the SI system, is a meter and kilometer. You know, if you use the British system, it's different. It's they call it circular mile and mile. You know, we'll talk about that one maybe toward the end of this chapter. You know, I'm not sure if I want to talk about the circular mile or not. That's the British English system. But SI system, you use the ohm per meter or ohm per kilometer. That's the unit they use for the resistance. Now the next one. Oh, conductance. Before going to the inductance calculation, there is no equation, there is no way to calculate this, but look at here. We have two towers. And this wire is going like this, right? To the next tower, right? So, remember we talked about the corona, right? What was corona? I said days like today, you know, for which there is a humidity, you know, we have water in the air, and if there is a high voltage transmission line, they're really starting to have some current going outside here, right? It's going to go through the air. And tonight, if you can find somewhere here high voltage transmission line, you can go look at this one. You should be able to see the corona. There is like a blue light, you know, around the wire. So basically, this is kind of, you know, if you look at it, kind of, you know, let's say this is the ground here, right? So this current is going from here. The current has to go somewhere, right? It can start from somewhere going to somewhere, right? This is, they call it leakage current. It's very small. It's very small. Don't get me wrong to think there is a huge current going like this, but this small current comes through here, right? Here we have a more higher density. You can see the blue light, but when you come a little bit further down, because of the kind of, you know, very wide open area, you don't see anymore, you know, that kind of blue light, you know. This is one. The next thing is, if you look at here, there is a kind of, you know, system like this, like insulator. These cables, they are connected to this. So this insulator, they are not a perfect insulator. They have some, you know, leakage current, right? If they get dirty, you know, sometimes not sometimes, though, it's because of salt. If you're somewhere close to the, like a hot area, and there is a, next to the ocean or rivers, you know, there's salt in the air. They're going to come on this one. Salt is a pretty good, you know, conductor, you know, but it's still not very. But the current is going to go through the surface of this one from here, and these towers, they are all grounded. The current is going to go through here. They call it again leakage current. Here, this is a leakage current. It goes through the surface of this insulator. So my point is, there is some current going from the system, the voltage of the system, the hot wire to the ground, right? They model this one, this path, the value of the resistance of this path. They call it conductance. But all the time we ignore this one, because first of all, it's very small, very small value. The current, leakage current, is very small value. And second of all, it's very difficult to calculate. You know what I'm saying? It depends on the environment condition. Depends to what temperature of you are. How much humidity we have in this one. How far we have from the ocean. How much salt in this one. How often they raise this, you know, they clean up this, you know, insulator. So it's very difficult to calculate that one. But they call it conductance. If you hear about the conductance, so there is a resistance, there is a conductance, and there is a capacitance and inductance. Those are these four parameters for every transmission line we need to calculate. Resistance, we said how we can calculate it. Conductance, we said there is no way we can calculate it, but some people, they show it in the model. We cannot calculate that value. Now we're going to get to the second, the third item, is the inductance. We want to see how we can calculate the inductance for a transmission line system. Inductance. I want to start with a single wire. I think we calculated before, when I started the transformer, but we're going to look at it a little bit different, So let's say I have a conductor like this. And there is a current going through this conductor, and I assume the current is evenly distributed around this area, on this surface, right? There's a current going there. Let's say the current is I. I'm not sure what you call it, I or yeah, call it I. Let's say the current I is going here. Now we want to calculate the inductance of this wire. Let's assume this one is the center of this. So there are two inductance. And we know from what I said, inductance is a result of flux, right? Whenever we have a flux and lambda, the inductance is lambda over I, right? So wherever we have a flux or lambda, we're going to have inductance. There are two parts of when this current is going through here, it creates some flux inside this conductor. It creates some flux outside of this conductor, right? So the one we are familiar with, the one is outside. We say the current is going. I didn't use this hand. We say the current is going this way, and the flux outside is like this, right? We say this is the. Let's put it here. This is the flux, right? It's going like this, right? But inside the conductor also there is some flux. We are going to calculate those things to see how much we call it internal flux and we call it external flux. External means this is outside, the flux going here, and internal what we have inside this one. So the total inductance is going to be L internal plus L external. We calculate each one just separately. Now let's get to this one. Remember we said integral of HDL is equal to I net. Right? I net or the current inside the loop, right? Wherever we consider the loop, for example, if you remember in the transformer, we said like this, right? We said if you're going to write the HDL, we said, okay, this is the, for example, the loop we have, right? So HDL is going to be NI, right? Because this current is I, right? And we have an N current, it's going to be N times I, right? The current inside the loop is going to be NI. But when we had only single wire, right? We said how much is the I net? HDL was just I, this current, right? Because there's only one current going that way, right? Now let's look at here. I'm going to go inside this one. The radius of this conductor is R. This one is R. I'm going to go select another circle inside this one. Let's assume this radius is X. And now we will go a little bit further. This is the dx. Right? Now, and we call the h here, and let's call here hx. Whatever is the value of the h, we call it hx on this circle inside the conductor.
Can you draw larger?
Huh?
Can you draw larger pictures?
Actually, to be honest, I was going to use the slide for this part. It would be much easier for me because I don't have to draw any picture or anything. But I don't know what it is. So I'm going to put the big conductor here. This is the conductor, and this is the length of the conductor, right? And you say the radius of this conductor is R.
Can you use a different pen?
What color do you like?
Black.
Because what color do you like?
Something dark.
Black. Darker, black. Blue.
I don't have black. I have a blue, red, and green.
Green works fine. Put pen orange.
So the radius of this conductor is R.
Oh no. That's not cool.
Now we have a problem. Somebody doesn't like the blue. this circle is x, I want to calculate hx here. Because I call it hx because it's the radius of x. I call it hx. Why I'm calculating hx? Because if I calculate the hx, I can calculate the b, right? B is equal to mu h, right? If I calculate the b, I can calculate the phi. Phi is b times a, right? If I calculate the phi, I can calculate the lambda. Lambda is the number of turns. Here there is no turns. We need to talk about that. But in general, it's the number of turns times the phi, right? So basically, I'm going to start from h. To calculate the h here, I can go further and calculate the lambda and finally calculate the error. Let's assume there is a little bit increase here. And this one, they call it, I'm going to write it big here, dx. It's the dx and this is the x, right? Let's write the integral. Go through the integral here. So we say an integral of h dl is equal to I net. So on this circle, h is fixed. So it can come out from the integral. So basically, this one is going to result in h times, how much is the integral of dl over this? Sorry, dx is going to be here. I made a mistake. Dx is here. This is the dx. Not that. Dx is here. Dx is here. How much is the integral of dx over a circle?
2 pi x.
2 pi x, right? How much is the I net? Can somebody tell me how much is the I net? I have a conductor, let's look at it this way. I have a conductor, right? The radius is r. I know the current all over here. How much is it? The current going to this conductor is I, right? Now I have another circle inside this one, and the radius of this one is x. How much is the current here? I know in the whole conductor I have I. How much current is going here? And I am assuming the current is uniform. Current distribution is uniform. How much is it?
Pi r squared minus pi r squared.
Is it, can I say x over r to the power of 2 times I? Yeah, actually I'm putting this area divided by whole area, right? Times I, right? That's what I'm calculating, how much current I have inside this circle with the radius of x, right? So this is my I. So basically H is going to be xi over 2 pi r, right? This is the H inside the conductor.
Should r be squared?
Huh? Yes. You're right. This one should be squared. It should be squared. 2 pi r. Now, and the unit is ampere per unit. Now I know how much is H. I can go calculate B. B is easy. How much is B? B is mu H. So I assume the permeability of this conductor is mu, because I'm going to use that one to calculate the B value. E is going to be EX is going to be mu HX. And mu for copper, for aluminum, those kind of things, mu is equal to mu zero, mu zero. Mu and mu zero, they are the same, but I'll keep mu. Now I have the B. I'm going to go calculate the calculate the phi. How about this one? Is it better than this one? So basically it's going to be, how much was the h? H was the xi over 2 pi r squared. So it's going to be mu 0 I over 2 pi r squared, right? Times what? Times x. It's going to be the b. Now let's go calculate c. As I say, I'm going to calculate L. See what I started. I calculate h. H I calculate b. B I'm going to calculate phi. Phi I'm going to calculate lambda. Lambda I'm going to calculate L. Right? Lambda over I is L. Right? So I'm going to calculate this. After b we need to calculate phi. How much is it phi? D phi. So again, now look at here. When you're going to look at the phi is always, when we have a cross section, let's say we have a donut core here, and this is the cross section of this one, this is A, right? And we have a B going this way. Phi is B times A, right? B times A, right? Now look at it here. We have this one, right? If I want to calculate the phi is going to be this one. It's going to be a little bit like this, going all the way like this, and this is the dx. And we are going to calculate it for 1 meter, for the unit length of the wire. So basically, d phi is going to be b. How much is the square area of this rectangle? It's going to be 1 times dx, right? If you have a rectangular, A, B, how much is this area? A times B, right? I have this element here, the thickness is, not the thickness, the width is dx, the length is 1 meter. I'm calculating the inductance for the unit length of the wire. The inductance I'm calculating is going to be for 1 meter of the cable. So this one is a 1 meter, right? This one is a dx. How much is this area? It's going to be dx, right? So I have the area is a dx. How much is my flux dphi? It's going to be d times dx, right? So dphi is going to be times dx. Be careful. This dx has been 1 times dx, right? Because dx by itself is a length. It's not a square area, right? Don't get it wrong. It's 1 meter times dx, which the unit is going to be a square meter, right? Just follow the dimension. My point is, it should be a square meter, you know. And because we are calculating for the unit length, you put 1, and you don't see the 1 over there. Now I have the phi. The next thing I need to calculate is the d lambda. D lambda is going to be x over r to the power of 2 times d phi. And let's say, how much is the d phi here? D phi is going to be mu 0 I over 2 pi r squared x dx. So why I put this one? Because again, look at here. If we have the total R, the area is going to be proportional to R squared. Now I'm calculating for x, it's going to be proportional to x squared. So basically, my point is how much of current I have. Remember here when I talked about the transformer? I said, let's say this is phi, right? And this is n. We say lambda is n phi, right? basically N kind of represent how much current I have, right? How much current I have here in this loop. Here, look at here. I think it's somewhere. Here. This is how much current I have in that loop, right? So basically, the gain is going to be x over r to the power of 2. So now I have my d lambda is going to be mu 0 I 2 I R2 is going to be R4, right? Mu 0 I and x3 dx, right? So this is my d lambda. Now I need to calculate the lambda. How much is lambda? How much is the lambda? It's going to be integral of lambda internal, int. Put it internal. I mean this is inside the conductor we are calculating. Lambda internal is going to be integral of d lambda, right? Which is this value, mu 0 I over 2 pi r4 x3 dx from where to where? If I want to calculate the whole flux inside my conductor, 0 to r, exactly. See, it's going to go from here to here, right? It's going to be 0 to r. If you calculate this one, lambda is going to be half of 10 to the power of minus 7 r. Weber turn over meter. This is for 1 meter of the cable. Just 1 meter. Keep in mind, this is for 1 meter I calculated. So I replace basically the mu 0 with a 4 pi times 10 to the power of minus 7. And you have the pi and 2 pi, they're going to get cancelled. This one is going to be x4 over 4. And you have 1 over r4. You do the integration, you're going to end up with this number. Now, how much is the L? If I want to calculate L internal, how much is it? It's the Weber term. You know what it's coming from where, right? We say lambda is NP. What's the unit for phi? Is Weber, right? Weber. You can remember that one from transformer. N is the number of turns. They call it Weber turn. And I do it over 1 meter because I'm calculating this one for 1 meter of cable. Yeah.
What is the little b?
No, this is not little, it's 10. It's
Oh, okay.
10 to the power of minus 7. 10 to the power of minus 7. You know, you don't have to worry about this simple. I don't want to jump to the equation and say, hey, this is the inductance value. I'm going to go through this one, you know, but at some point I'm going to jump. I say, hey, this is the equation. If you want to see the proof, you can go look at your book. But I don't want to put the equation on the board to say this is the for example, inductance of the conductor. You know, you are going through this process to learn it how you can calculate this. Now, see, I said when you have this one, right? You say lambda is equal to n phi, right? This n kind of represents the number of current, you know, number of turns you have here. If there's a current going through that, right? If I had only one here, if I had only one turn, right? It's going to be one, right? There is one current going through, right? If I have 10, there's 10. Because the flux, the lambda is going to increase with the current, right? The more current, the more lambda, right? Now look at here. I said look at here. I want to calculate the lambda, right? I want to relate the phi to the lambda. I'm saying how much current I have here. How much current? This one is going to tell me how much is the lambda, right? So I know overall I have R. How much current I have here is going to be x over r to the power of 2, right? And the x over r in this case is similar to n. Basically, it plays the same rule as n plays. Now, lambda value how much is the L internal? Is the lambda internal over I, right? So it's going to be basically 2, not 2, 1 over 2 times 10 to the power of minus 7 Henry per meter. This is the internal inductance of the wire. This is the internal inductance of the wire. Now, there is some flux outside also, right? Let's calculate that one, We calculated the flux is inside this one, right? There is some flux outside. Let's calculate the L external. I want to calculate the L external. This is simple. I'm going to calculate H, B, phi, lambda, and F, right? How much is the H if I have this one? Now I'm going to go outside of this one. I'm going to go outside, for example, here. I'm not sure what you call it. Let's put the X again. I believe you called it. Let's say I want to calculate the D1 and let's say consider another circle here. D2. I have 2 points, point D1 and point D2. I want to know how much is the inductance here. Because these are both outside of this conductor, right? There are some flux going through here. I want to know how much is it from here to here. Later on, I'm going to say, okay, D1 is going to be here, I'm going to put it on here, right? And D is going to be D, whatever. Distance from this wire, I can say how much it is. Now, I want to calculate the inductance for here. I'll call it L12, for example. So from D2 to D1, I want to see how much inductance I have over here. To calculate that one, again, let's assume here, for example, somewhere here, we have, this is the hx again, right? And this is the x. So again, I can say integral of h dx is equal to what? Equal to I net. How much is the I inside this red loop? How much is the current inside this one? This is I, right? Because the conductor is completely inside this red loop, right? So I net is going to be I. Hx, let's call this one Hx. So H is constant, is going to come out. H is constant, I mean on this loop. Everywhere on this loop, the H is constant. If you come here, H is not the same with this one. But on this circle, everywhere the H is the same, So how much is the integral of the dx on this loop, on this circle? It's going to be 2 pi x, right? It's going to be 2 pi x is equal to I. So basically hx is I over 2 pi x. How much is b? Is outside mu0 hx. So it's going to be mu0 I over 2 pi x. How much is it dphi? It's going to be dx. Again, dx. Be careful. dx again is 1 times dx, right? So dphi is going to be mu0 I over 2 pi x dx. How much is the d lambda in this case? How much is the d lambda? Why did I put the d 1 times dphi? Why?
Because when you integrate, you have to.
No, the last time I did it, remember, I was inside this one. I want to see how much current I have here, right? No, I am here. I have all the current, right? How much is it? Is I, right? The ratio is 1. Last time I was partial of this current, right? Based on how much is this x, the current is going to change. How much current I have inside this circle, right? Now I am here. So it's going to be times 1. Basically, if you look at it here, it says x over r. As soon as you go outside of the conductor, this x is equal to how much? As soon as you are outside the conductor, x is off, right? Because you are either just here or here or here. There is no difference, right? For all of them, the current inside the loop is going to be how much? It's going to be I, right? So d lambda is going to be equal to mu 0 I over 2 pi x dx. Now I want to calculate the lambda. Now I want to calculate the lambda. And going back here, this d1 is the distance to this center, and this 2 is the distance to this center. That the point number 1, the distance of the point number 1 to the center of conductor, we call it d1. The distance of the point number 2 to the center, we call it d2, right? Now, how much is the lambda 1, 2? Lambda 1, 2 means how much flux turn we have here in this area. I want to see how much flux turn I have in this area. So what should I do? I should take an integral of lambda from d1 to d2, right? So basically, it's going to be integral of d1 to d2 mu 0 I over 2 pi x dx. If you do this calculation, basically dx over x, mu 0 I and 2 pi, they are constant, they all come out from the integral. So dx over x, the integral of that one is ln of x, right? dx, you know this one from calculus, right? dx over x is ln of x, right? So you don't need to learn this. I say I don't want to jump to the conclusion. You know, I have to go through this one to get you to the final answer I need to have. And I want you to know the final answer. You don't have to know the proof of this one. This is a little bit of electromagnetic and those kind of things. If you know it, it's better. If you don't know it, doesn't matter. You know, it's not that kind of critical. As far as you know how to calculate the inductance of the cable, that's enough. You know, which is the last equation, you know. And I forgot to say, for the next week, you can bring a cheat sheet. One side, one page, both sided. But usually my exam are not cheat sheet dependent, you know. If you put all your notes on the cheat sheet, bring it here. If you don't know what you're putting there, it's not going to help you at all. You have to learn it, what you're putting there, you know. But you can bring one sheet, both sided for the next week, you know, and for the exam. So this one is going to be ln of x, right? So basically, it's going to mu 0 is a 4 pi times 10 to the power of minus 7. It's going to be 2 times 10 to the power of minus 7 I ln of d2 over. This is the lambda. Now, how much is L12 if I want to calculate L12? This is not mutual. Don't get it wrong with the mutual inductance. This is the inductance between the area of the D1 and D2. It's going to be lambda 12 over the current. So basically, it's going to be 2 times 10 to the power of minus 7. I is going to cancel. And D2 over D1. Okay, so we calculated the L. I calculated L internal. Now I want to calculate the L external. External means start from this point, right? From this point all the way, right? A distance of D. So L external, I call it LEXT. For the conductor is going to be, how much is the D1? D1 is R, right? As soon as we go outside the conductor, right? So it's going to be 2 times 10 to the power of minus 7 ln of, and I call the D2 D. So I have my conductor here, the radius is R, and I have a point here D, if I want to know how much is the L external, is going to be 2 times 10 to the power of minus 7 d. D is this distance over R. This is my external inductance.
Is Ln just like a property of the wire, or?
Is a property of what?
What is Ln?
And logarithm, natural logarithm, right? You know that.
Oh, so it's E?
Yeah, it's a you are
Oh,
familiar
yeah.
with E and those kind of things, right?
Gotcha.
E and Z to the power of x, for example, ln of x, those kind of things. You know about this thing, right? Yeah, that's a natural. They call it natural logarithm. They have a log 10. Usually they use this one, they don't put the 10 here. By default it's there. But when they say ln, E is 2.7 something. I cannot remember the rest. This basically is a logarithm to the base of this number.
I just thought it was like another inductance or something.
No, that's the ln. That's the ln we call it ln. What do you call it ln? You call it ln, right? Yeah. So I thought maybe you used a different term for that. So we calculate L external. Now how much is the total inductance? L is going to be L internal plus L external, right? So basically it's going to be 1 over 2 times 10 to the power of minus 7 plus 2 times 10 to the power of minus 7 ln d over r. Now let's simplify this equation a little bit. Oh, I forgot here. This is a Henry per meter again. Keep in mind. This is a per unit length for 1 meter of the cable. Now, L is going to be, I'm going to factor in 1 over 2 times 10 to the power of minus 7. So the first one is going to be, or maybe 2. I mean, factor in 2. Yeah, 2. Sorry. Let's factor in 2. So basically this one is going to be 1 over 4 plus ln of d over r. 1 over 4 on this one. I'm going to write it ln of e to the power of 1 over 4. Is it correct? ln of e to the 1, you know in general, L logarithm ln whatever, ln a to the power of b is equal to b ln a, right? You know this one. So basically this is 1 over 4 coming here, ln of e is 1, right? 1 over 4 times 1 is going to be 1 over 4. So, and you know ln or logarithm doesn't matter. A times b is ln a plus ln b, right? These are a few rules from logarithm, you know from your maybe high school. I'm not sure. We used to learn this one in the second year of high school. You used to learn all this in the second year of high school. So this is a ln a, this is ln b. So it's going to be 2 times 10 to the power of minus 7 ln of this a times b is going to be d times e to the power of 1 over 4 over r. Again, I'm going to write this one like this. 2 times 10 to the power of minus 7 ln d over r e to the minus 4. This one, right? They call, so this one, they call it r prime. Equivalent radius of the conductor. So basically, it's going to be 2 times 10 to the power of minus 7 ln d over r prime. Henry per meter. How much is the r prime? Is the e to the power of minus 1 over 4 r And this number is a 0.788, I believe, something like that. Yeah. So basically, this is a 0.7788R. This equation is the final equation. This is what you need to know. The inductance of a single wire is going to be 2 times 10 to the power of minus 7. I want to find it. I have a wire here. I want to see in the distance D, if I am standing here, how much is the inductance of this system? So the radius of this wire is R. The equivalent resistance is going to be this one, 0.7788 times R. So the total inductance of this system is going to be 2 times 10 to the power of minus 7. D is the distance to this wire, to the center of this wire, divided by R. This is what you need to calculate the inductance of the wire. It may happen in future, for example, I'm going to calculate 2 wires, because usually we don't have a single wire, we have 2 wires. You need to calculate that inductance. For example, myself, I was going to, one of the things is important in power electronics is this. Look at it here. For example, you have some switches here. I don't want to get into the detail. And this one, this is, for example, the 3-phase inverter. And here is the output. And this is the output. But here is the input. And you have a battery somewhere here. You want to connect this one here. Right? You want to connect this battery. The inductance of this wire is very important for this system. Just I need to calculate this one. I'm not saying this equation is going to give me exact value, but it's going to give me a very good approximation of how much inductance I have in my system. And I can calculate whatever I need to calculate. So basically, you can use this equation to calculate the inductance of one wire. But we are going to get into 2-wire system, because usually we don't have 1 wire. We have either a single phase, the 2 wires, or it is a 3-phase. We have 3 wires. We'll get to all those when we have to calculate them. Now, the next one is now if you have a multi-wire system. I want to see how we can calculate the inductance. Yeah. Now let's consider this. Let's consider we have how many wires we have? One conductor number 1, conductor number 2, conductor number K, and we have the conductor N. This is number N, and this is the conductor number. We have M capital conductor. I don't know, 100 conductors. I don't know, 50 conductor, whatever we have. And there is a point here is P. I want to calculate the total inductance of this system. I want to, using what I did here, I want to calculate the total inductance of this system. Let's use some, this one has the I1, this one has the I2 current, this one has the IK, this one has the IM, and this one has the IB. We have an M conductor, and each one they are carrying on some current. The only thing that is important here, all this current together, sigma IM, from M equal to 1 to N is equal to 0. All this current together, they're going to be adding together is going to be 0. There is a reason we are putting that one. Just let me tell you the 0 why I'm saying this one is equal to 0. If you have a 2-wire system, right? Let's look at a 2-wire system. Let's say this is a 2-wire. We're going to go next, we're going to go to this one, right? If I have a single phase system, 2-wire, right? Single phase has a 2-wire, right? If this current is I, how much is this current? Is I this way, right? The current goes that way, come back from here. Or I can say the current this way is how much? Minus I, right? So basically, if you add these two currents, minus I is 0. If you have a three-phase system, you know that one. IA plus IB plus IC is how much? 0. For balanced system, IA plus IB plus IC is 0. So this is the only condition we have. Adding all this current together should be 0. That's the only condition we have here. We'll talk about this one next. Now, I'm not sure if we will go through the proof or not, but let's put it this way. Let's say this is this distance, let's call it dp1. This one is going to be dp2. This one is going to be dpk. This one is going to be dpn. And this one is going to be a distance. Again, dp capital. And let's consider from this conductor to the other conductor, this one is, we call it dkn. From this conductor to this conductor is dkn. For example, from here to here is d12 or d21, whatever, we can solve. From here to here is dk2, for example. The two conductors, doesn't matter, they don't have to be next to each other. You know, the distance between the two conductors, you know, for example, conductor 5 and the conductor 10 is going to be d5, 10, right? 5 and 10 shows the number of conductors, what's the distance between them. So if we have this one, I'm not sure go through the, do you want to go through the equation, how we get to the final answer, or you're okay if I can put the final answer there? I can go either way, you know, I can explain it how we get there, or I can put the final answer there and we jump this one. I think I'm going to jump, you know, because it's going to take time, to be honest, first of all, and I'm not sure how much you guys will follow the process, you know. But if we have something like this, let's look at it. We have a multi-conductor system, right? I want to see in this point P, how much is the total inductance? Keep in mind, total inductance is for this one, how much inductance I'm going to get from this one, how much I'm going to get from this one, how much I'm going to get, all of them together, right? We calculated only 1 year. We calculated 1 year. But now we have n of them. We want to calculate the total inductance. If you calculate the total inductance, this is the equation in page 182 of your book. We call it, not 182. We call it lambda k. So lambda k is going to be 2 times 10 to the power of minus 7, look at here, same thing here. Sigma from n equal to 1 to n, ln of 1 over dkn. What is the dkn? Look at here. Distance between this, distance between this, distance with this one. So you can write this one, you know, for all of them. If you want to see, can you read it here? I said 2 times 10 to the power of minus 7, n from 1 to n, because I have an n conductors, right? I'm going to go one by one. In, for example, when n is 1, it's going to be I1, this one. When n is 2, it's going to be I2, I3, I4, go all the way, right? So times ln of 1 over dkn. For example, when k is 1, let's say k is 1, right? So it's going to be 1, 1, d11. What is d11? What is d11? R prime. D11, let's define it this way. The distance of the conductor to itself. Not somebody else. You know what I'm saying? No. So what we called it here, R prime. Here. This one. Is the D1. How much is the D22? Let's assume this one, the radius of this one is R2. So it's going to be how much? R prime 2, right? D33, R prime 3. But usually all these conductors, they have the same radius. All of them, they are R. Basically, D11, D22, D33, D44, all of them, they're going to be R prime. And how much is R prime? Is 0.7788 R. You can look at all this, all this system. It's not like that. One of the strands is bigger or the other one is smaller. They are all the same. My point is, all of them, they have the same cross section, right?
So for the EKM always is on the right side, the M is the
M is my index here. I'm changing it. It's going to go, a small m is going to go 1, 2, 3, 4, 5 until n. Maybe I should have used I, so that get you confused. If you don't understand, it's going to make this one I and make this one I also. So it's going to go from I equal to 1 to II to EKI. Yeah, that's what I would do. It's small n over there. And the book uses small n, maybe it will confuse it. But it's the index, we change that one. Now, yeah.
what is R
R prime is this one. For a conductor with a radius of R, R prime is R times this number. 0.7788 is equivalent kind of radius of this conductor. Now, we say if you have a multi-conductor system, the total slot between this one and this one is going to be calculated this way. If I want to calculate for this one, it's going to be lambda 2, right? Lambda 1, lambda 2, lambda 3, I can calculate all of them, right? Now, I cannot calculate inductance. Can you tell me why? Because they have different currents, right? All of them, one is I1, one is I2, one I3, but if I divide it by IK, it's not going to give me a kind of, clear equation. But keep this equation now, we are going to move on to the two-wire system. Let's move on. I'm going to use this equation to calculate the inductance for the two-wire system. So, now we have this system. I have a conductor X and I have a conductor Y. And this is all, whatever I'm calculating, they are all per unit length. For example, again, this one is going to be Weber turn over meter. Just keep in mind, I'm calculating this for 1 meter of the cable. If you have 100 meters, you time it by 100, right? If you have, 1 kilometer, you time it by 1,000. You get those numbers. Now, I have two conductors. Let's say the current in this one, this is the Rx. Let's say the diameter of this one, the radius of this one is Rx, and the radius of this one is Ry. What we said over there, we said the only condition was sigma I should be equal to how much? 0, right? Let's say Ix is equal to I. We are going to get to the better part. This is just a kind of, deriving this equation. After we derive this equation, we are going to only use the result. Maybe today or I'm not sure. Next week we are going to get to some examples. You can see, I'm not going to use any of these things here. Just I want to find the final answer to calculate my inductance and all those kind of things. So, if I call this one IY, how much is IY? How much is IY?
Minus I.
Minus I. Why? Because we said sigma of the total current should be how much? 0. Now I have these two wires. They are located distance of D far from each other. You want to calculate the inductance of this system. This is something you see in your normal life. You have a two-wire system, right? A single wire. You want to see how much is the inductance of that cable, that wire. How much is it? You can calculate it using this equation here. Now I'm going to go back here. Basically, instead of having, N conductor, how many I have? just two conductors now, right? So I can go calculate the lambda 1, basically lambda x, conductor x. I can calculate lambda y, conductor y, right? I can calculate the inductance for this wire. I can calculate the inductance for this wire and add them together, right? I can calculate Lx, I can calculate Ly, and add them together. It's okay. The total inductance is Lx plus Ly, right? So I calculate lambda x first, right? If I calculate the lambda x, I can calculate the Lx. Lx is equal to lambda x divided by Ix, right? Lx is lambda x over Ix, right? And Ly is lambda y over Iy, right? And L total is Lx plus Ly, right? So now using this equation I have here, I calculate the lambda x and lambda y, and I say calculate the Lx and Ly separately, and I put it here to see how much is the total inductance. Now let's see how much is lambda x. If you look at this equation, it's going to be 2 times 10 to the power of minus 7, right? 2 times 10 to the power of minus 7 times. So we have two conductors. We have a conductor x and we have a conductor y, right? So let's see. So it's going to be Ix, right? When I is 1, it's conductor x, right? It's going to be Ix times, it's going to be Ix times ln of 1 over what? Somebody tell me, what's that?
D.
Huh? dy. Let's see. Here I say dki, right? So how much is, what is the k?
1.
X. So it's going to be dx. I is going to go from x to y, right? So it's going to be dxx. The first one is going to be dxx, right? It's going to be dxx. dxx plus iy. The second one is going to be iy, right? Here it's going to go to the next one. We went from the x, we put the x here. X is the number 1, right? Y is the number 2, right? So it's going to be I2, which is Iy, right? It's going to be Iy times ln of what? It's going to be k is 1, right? Which is x. Now I is 2, which is y, right? It's going to be dxy. Right? Now let's replace this. How much is the dxx? Dxx. Yeah. How much is Ix? Is I, right? Ix is equal to I. How much is the it's going to be I ln of 1 over r prime x, right? dxx is r prime x, right? How much is the radius of this one? But prime. But prime. Keep in mind. How much is the I1? Minus I times ln. How much is the dxy? D. So lambda x is going to be 2 times 10 to the power of minus 7 I ln of d over r prime x. Am I correct? So it's going to be, yeah, it's going to be this one divided by that. 1 over r prime x over 1 over x, d over. So how much is the Lx? How much is the Ix? Ix is I, right? This one divided by I is going to be 2 Now k is 2 or y, right? It's going to be 2, sorry, this one is going to be 1, which is means ix, right? It's going to be ix, let me write it here. This one is going to be ix ln of 1 over what? Dxy, right? Plus plus iy times ln of 1 over dyy. Let's replace ix with minus iy, right? Ix is a minus iy. Or we can replace both of them with I, doesn't matter. But let's put it this way, it's easier for you. You say ix is minus iy, right? Ix is minus iy. So if you replace this one here, factor in iy is going to be 2 times 10 to the power of minus 7 iy times ln of how much? This is a minus this time. This is again d. This one is r prime y, right? So this one is negative. That one is going to be positive. It's going to be that one divided by this. That one divided by this is going to be again d over r prime y. How much is the ly? How much is the ly? How much is ly? Is this one lambda y divided by iy. So iy is going to cancel. It's going to 2 times 10 to the power of minus 7 ln of d over r prime y. Henry per meter. How much is the total inductance? LP or LP. Lx plus Ly. Let's put them here. It's going to be 2 times 10 to the power of minus 7 times ln of d over r prime x plus ln of d over r prime y so is equal to ln A plus ln B, right? It's going to be this times this, right? It's going to be 2 times 10 to the power of minus ln of d squared over r prime x, r prime y, right? I'm going to write this part. I'm going to write it this way. The square root of r prime x, r prime y to the power of 2. Just I'm going to put it. I'm going to put a square root back to the power of 2, right? Now, let's put it here. L total is going to be 2 times 10 to the power of minus 7 ln of d over square root of r prime x, r prime y to the power of 2, right? Take the 2 out. It's going to be 4, right? It's going to be 4. So L total is going to be 4 times 10 to the power of minus 7 ln of d over square root of r prime x, r prime y, right? But usually, when we have a single phase system, you have a 2-wire system. Rx and Ry, they are equal, right? They are not different. One of them is not smaller, one of them is not bigger, right? They are usually the same. So if Rx is equal to Ry equal to R, which means r prime x is equal to r prime y is equal to r prime, which is equal to 0.7788 r. So here this equation is going to be changing to 4 times to the power of 10 to the power of minus 7 ln of d over r Henry. I'm going to stop here. I wish I could go one more page, but I have to stop here. So basically, the two wires I put in over there, you can model it like this. The equivalent of those two wires, you can put it like this. And you can calculate the inductance of the wire. How much is the inductance of the wire? So I'm going to stop here. I was going to calculate a three-phase system. Yeah.
So there's only an inductance in one of the wires? So
Inductance of what?
There's only inductance in one wire, the total?
No, I put together.
Oh.
This is LT is both. If you are going to write it down, it's going to be like this. LT over 2 and LT over 2, right? Just put it in one. Yeah, resistance is there. I'm not talking about the resistance here. Yeah, there is a resistance. You know, I didn't put that one here. Now we are talking about how much is the inductance of this wire. If you have a 10 meter of the wire, they tell you how much is the inductance. You can calculate. You tell them, okay, give me how much is the R of this wire. I can calculate the inductance of this wire. We'll go through a few examples. Now, I was hoping we are going to go a little further. I can solve some examples on this one, but we are going to post it for next Tuesday. Oh, we have an example. Thursday, if there is no pizza party here, I'm going to continue the discussion session, which I'm going to go some examples for this kind of system. You know, I'm going to go over some examples after the Thursday class. As I said, if there is no pizza party, you know, and otherwise we have to.
What will be covered on the midterm?
What covered on what?
What will be covered on the midterm?
Midterm we have started with a three-phase system, transformer. This is what we are going to cover in the midterm exam.
So,
But transformers, there are single-phase transformers, three-phase transformers. You are going to have one question at least. At least you are going to have 3 questions. One in a three-phase system, one in a single-phase system, one in a single-phase transformer, and one in a three-phase transformer. But because there is like 95 students in the class, I may break it down to 6 questions, but short, not A, B, C, D, you know. Just make it, you know, that way it's much easier for grading, you know. I may break it down in like 6, 7 questions, but no short part, you know, just one part to calculate, you know. But we have a single-phase transformer, three-phase transformer, and three-phase system.
Are there chapters in the book that are going to correspond to the material in the midterm? On the midterm?
Yeah, I think it's chapter, I think 2 and 3. They are about not maybe 100%, you know, maybe it does cover 70–80% of the material I said. Another 20% is maybe from other books, so it was not in the book and I covered myself. But I think 80% of the material is in the chapter 2 and 3. We will post the homework solution for homework number 2 hopefully either tonight or tomorrow night. Homework 3 will be posted the solution Thursday night. As soon as you turn in the homework, we will post the solution Thursday night.